Okay, come back to this linear algebra lectures. I will continue from the last lecture. Remember, last lecture we have proved that if V is a k vector space, k is arbitrary field, then we have proved that V has a basis. In case if V has a finite basis, then we will say V is finite dimensional. In case if V has infinite basis, then we will say it is not finite dimensional, or we will say it is infinite dimensional. But in this lecture I want to prove that any two bases of V have the same cardinality. So, the theorem I want to prove is the following theorem. If Vi I in I and Wj j in j are two bases, two k bases of V, then cardinality of I equal to cardinality of j. And this common cardinality, this common cardinality is called the dimension of V, usually denoted by dim kV. We have proved this theorem in case when I is finite. So, we have proved this. We have proved this if V has a finite generating system. Note that in that case we have noted that every basis is finite. Therefore, I is finite, j is finite, and further we have proved exchange theorem and thereby proving their cardinalities are equal, and that is the dimension in case of with this finite generating system. Today I want to prove this without this assumption, but before I prove that I need to recall precisely the results which concerns about the cardinalities of the sets in general. This is necessary because when we want to prove things more precisely, we should also know the definitions more precisely and their use. So, I want to recall basics of what is called as cardinal arithmetic. This is what the basic. Mostly I will tell the definitions clearly, and the results I will not prove that. Many of the results will need to use Zorn's lemma or axiom of choice. So, I will skip the proofs, but I will write the proofs in the notes. Okay, so let us recall. Okay, this is cardinal arithmetic. So, the idea is the following. So, first of all, before I start talking precisely, I will keep, to avoid the so called famous paradoxes in set theory, I will confine myself to saying that set of sets, and this means You see, if I talk generally, then we might land into paradoxes. So, this means that all my sets are subsets of a big universal set, which I will not mention what that big universal set is, but it is understood that all are subsets of some big sets, and so therefore for that I will keep using the phrase set of sets. So, for each element of this set, see, each element is a set and you have a collection of sets. So, to each element of a set or each set A, I am going to attach some object, which either I will write like this. There are several notations in the literature. So, either it is written like this, or it is written like this, or also written like this, and so on, but I will use this notation. So, what is it? First of all, note that in a finite case, if A is a finite set, that means there are finitely many elements, and crudely speaking, this number is called the cardinality of that finite set. But when you go to infinite case, this crudeness will not be sufficient. So, we will have to come up with better notation and also better definition. So, first of all, note in a finite case, if A is a finite set, then A there exists, let me write precisely this statement, then there exists a unique natural number n such that A to n star n is by definition 1 to n. Then there exists a unique n and a bijection, a bijective map, that I will denote sometime like this. So, note that this needs a proof, and the proof usually goes like this, that this proof is, so to prove this, what one need to note that if we have two natural numbers m and n, and if you have a bijection from n star n to n star m, bijection, then we have to conclude n equal to m. This needs a proof, and this one can prove easily by proof by induction on n. So, all finite sets are, we can identify under bijection with this subsets 1 to n. And note that when I say this, if n were 0, n star n is by definition is empty set. So, this I want to imitate and define concept of equipotency. Equipotent sets. So, you have two sets A and B, two sets, then A and B are called equipotent or they have the same cardinality, or A and B have same cardinality. If there exists a bijection, there exists a bijective map from A to B, F, and in this case okay, I will postpone this. We call them equipotent. Now it is very clear the following. Okay, clearly this equipotency is an equivalence relation on the set of sets. That means what? So, it should be reflexive. Reflexivity is clear because identity map of any set A to A, this is a bijection. So, A is equipotent to A. Transitivity, if A is equipotent to B, that means if there is a bijection from A to B, let us call it F. There is a bijection G from B to C, then we need a bijection from A to C, but that you can take the composition G compose F. Bijective composition of two bijective map is bijective. So, this shows that the equipotency is a transitive relation. Symmetry, if A is equipotent to B, that means if there is a bijective map from A to B, then F inverse exists and it is a bijective map from B to A. So, that means it is symmetry. That means it is symmetric. So, this equipotency is the equivalence relation on the set of sets. So, any equivalence relation we can talk about equivalence classes. So, the equivalence class of A under equipotency is denoted by either it is denoted by the symbol or also it is denoted by this or it is denoted by simply card. So, that is the equivalence class. So, now let us see in a finite case what happens. In a finite case, so this represent all the sets which are in bijective correspondence with A. So, in a finite case, a prototype of this equivalence class A, this is nothing but one representative we know very well, that is n star n, where this n is a unique, n is the uniquely determined natural number who we say the number of elements in A. This is in a finite case. So, you start, let us start few numbers. So, you see start with the empty set is finite, the number of elements is 0. So, it is empty set will give this, the empty set, this symbol is nothing but 0. We can identify this with n. For singletons, all singletons will fall in the same equivalence class, and that this is 1, and so on. All the sets which has precisely n elements will fall in one class, and that class is same as this class, and that is n. And we can keep doing this as long as the sets have finitely many elements. The first time you come to a set which does not have finitely many elements, that is the set of natural numbers, and that this is usually denoted by aleph naught. So, aleph naught represents all the sets which have cardinal, which are in bijective correspondence with the n, and then you can keep going it. So, like this. So, these are called, by abuse of language, these are called cardinal numbers, and we have studied the arithmetic in case of up to here. We have studied arithmetic. We have not studied, for example, how do you add aleph naught plus aleph naught plus aleph naught, whether what is the meaning of this, or what is the meaning of aleph naught into aleph naught. These we have not, this does not come in our arithmetic, and let us say finite arithmetic. But I want to now extend this arithmetic to arbitrary class. So, I should be able to talk what is their plus, what is their product, what are the rules, like our usual arithmetic rules, exponentiation and all other cardinal arithmetic can be extended to this setup, and the study, this study is called cardinal arithmetic. So, this I want to digress not so much, but little bit. So, for example, also we want to also extend the order, the usual less equal to order we want to extend to the this arithmetic. Okay. So, first of all I want to write, I want to first, if you remember, even when you studied the set of natural numbers, even before addition and multiplication, the concept of order was introduced first, and then it was used to study addition, multiplication and their relations with the order, the natural less equal to, monotonicity, etc., etc. So, I am going to imitate the same thing. So, for example, if A and B are sets, arbitrary sets, then I will write this less equal to this if there exists a bijective map, there exists an injective map from A to B. In finite case, it is clear that if there is an injective map, the number of elements in A is less equal to number of elements in B. So, this makes sense, and instead of writing this, I will also use the notation A this. So, I have defined this. This is a relation on set of sets. And in this case, we will also say that the cardinality of A is smaller or equal to cardinality of B. So, we will also say cardinality of is smaller or equal to cardinality of B. Now, since we have done injective map, we can also do the similar thing using the surjective map. For example, we can translate this. So, note that this relation, what I said, it is, so what are the properties for this relation? These relation properties are, it is reflexive. Reflexive is very clear. Identity map is injective. and transitive. Because if you have a injective map from A to B, injective map from B to C, then the composite map is also injective. But what is not true is symmetry is not clear. Symmetry is not true in fact. So such a thing, such a relation is usually called a pseudo order. This is a pseudo order on set of sets. So one can also characterize this reflexive relation by using surjective maps. For example, one can easily prove. So if A is a non-empty set and okay, then A, this symbol B, let us call it script less equal to, if and only if there exists a surjective map from B to A. This also needs a proof, but this is not too difficult. I am going to leave the proof. All the proofs I would add it in the notes. So now if you have a pseudo order, then you can make it an order by pushing in more things. So and the order will correspond to an equivalence relation. So 1 minute, okay. Okay, this is an order, but the order is not an equivalence relation. Sorry, we have to make sure that it satisfies antisymmetry. So to make it antisymmetric, we need like this: A less equal to script less equal to B, and B less equal to A. Then we want A equal to B. We need something like this. So we push in, see, each pseudo order you can make it an order by pushing in this property. So the associated order to this pseudo order, so that I will denote so that means what? That means I have enlarged this relation and make it order. So that one I want to denote by, is denoted by this. So what is the definition of this? Then when say that A tilde B, if and only if A script less equal to B and B script less equal to A. So that is how we have extended this pseudo order to an order. So this is our relation now. So in other words, let us spell it out what it means. A tilde B, if and only if there is an injective map from A to B and also there is an injective map from B to A. So this is if and only if there exists injective map from A to B. This was the definition of this script less equal to, and there exists injective map from B to A. Then we will call them A tilde B. Now obviously if you have this, then A and B have the same cardinality, that should be proved, and this is precisely was conjectured by Cantor but he did not give a full proof, and the proof was given by Bernstein, B-E-R, Bernstein's theorem. It says that if A and B are two sets, if A, this script less equal to B, and B script A, then A and B are equipotent. In other words, if there is an injective map F from A to B and there is an injective map from B to A, then there is a bijective map from A to B. This means the cardinality of A equal to cardinality of B, or A and B represent the same equivalence class. This is very important theorem of Bernstein. It is also called, sometimes some books give a Schroeder-Bernstein theorem. The same, or Bernstein's equivalence theorem. So, this is what is very important. It tells you how do we check that the two sets have the same cardinality. To check that the two sets have the same cardinality, what we need to produce is an injective map from A to B and injective map from B to A. Then they have the same cardinality. This is what we will need to use to prove our two bases have the same cardinality. Okay. This Bernstein theorem, there are many proofs. The standard proof I will write in the notes, and also a slick proof which uses fixed point theorems, etc., that I will mention it in exercise. Let us come back to our proof that vector space basis. Okay, so coming back, remember we want to prove the following. We have one basis xi, I in I, and yj, j in j. There are two k bases of V. And what are we assuming? We assume I is not finite. Remember, when I is finite, we have noted J is also finite and they have the same number of elements. This is precisely the finite case we have proved, and that is proved by using the exchange theorem. Now, I is not finite. So, then first thing to note is then J is also not finite. Because if a vector space has a finite generating system, then it will have a finite basis, and one basis is finite, then all bases are finite. So, if one basis is infinite, then all bases are infinite. So, both I and J are not finite sets, and we want to prove that cardinality I equal to cardinality J. But for this, what we need to prove is, so for this we need to prove that, or need to produce injective maps from I to J and J to I. Because if there are two injective maps to this, then there is a bijective map also. So, that means the cardinalities are equal. So, our job is to prove now there are injective maps from I to j and there is injective map from j to I. For this we need to use John's lemma, but John's lemma is applied not directly, but using John's lemma we first prove the following assertion, which I will not prove, but I will state clearly. The first assertion one proves by using John's lemma is if A is any infinite set, then the cardinality of A cross A is same as cardinality of A. So, this means there is a bijective map from, so that is there is a bijective map from A to A cross A. There exists a bijective map from A to A cross A. So, this is a simple application of John's lemma, that I will not do the proof here. Okay, then second observation I will need to use is, if you have a X is infinite set, and yi is a family of sets, family indexed by set I, where cardinality of I is not more than cardinality of X. Again, this means there is an injective map from I to X. Then the assertion is cardinality of the union is less equal to cardinality of X, and this inequality can simply be deduced from 1, this one. So, both these I will not give the proofs, but use this to prove this cardinality I equal to cardinality J. Okay, let me finish this proof and then we will stop. Okay, this is very simple. So, now what we have given? We have given that xi is a basis and yj is also basis. Now, fix j. So, for every j in j, this means for every j in j, this vector yj, I can write it as a finite combination of this xi family. So, this is summation aij xi, this sum is running over I, and tuple aij where I is varying, this tuple belongs to k power round bracket A. That means only finitely many, for fx j only finitely many aij's are non-zero. So, you look at the set Ej, this is by definition all those i's, I in I, such that aij is non-zero. This is a finite subset of I, this is a finite subset of I. Since Ej's are finite, we will know that okay, all these are finite subsets of this, and I take their union to be I prime. I prime is the union of Ej's, J is varying. Now, this union is indexed by J. Therefore, by the observation 2 above which I listed, cardinality of I prime will be not more than cardinality of J. This is one thing, and another thing is, if I just take only all xi's where I varies in I prime, this is a generating system. Because once I have this all these indices I, then I capture all yj's. So, the subspace generated by this will contain all yj's and therefore, it will be a generating system. See, this is because it is a generating system for V, because yj belongs to the subspace generated by this xi I in I prime, but this therefore, subspace generated by yj's will be contained in subspace generated by xi I in I prime, j in j, but this is already V because yj is a basis, therefore, this has to be V. So, that implies this, the generating system. But you see, this was the basis. So, you cannot drop any element from a basis. So, that only says that proves that this I prime, this must be equal to I. That means this I prime has to be the whole I, and cardinality I is less equal to cardinality j. We cannot drop any element from I to get a generating system for this. So, we have proved cardinality I is less equal to cardinality j. Now, I interchange the roles of the basis. So, by interchanging the roles, we get cardinality j is less equal to cardinality I, and then Bernstein theorem will tell you then cardinality I equal to cardinality j. This is Bernstein. So, this gives a complete proof of the fact that any two bases have the same cardinality modulo those two results which I quoted, which is a consequence of John's lemma. Okay. We will take a break and come back after the break. Thank you.